All right, so now we're going to talk about problem 10 in chapter 18. Problem 10 is actually a fairly difficult problem. And so I wanted to go over this to give you the opportunity to learn more because this is a good problem to learn a lot of different things from. All right, so first, just to start off, this is an equilateral triangle, right? Because it's an equilateral triangle, we know that all of these angles are 60 degrees, right? Every single one of those angles is 60 degrees. So that's going to help us later when we start talking about the vector portion of this problem. Okay, now we have these three charges. We have QA is 2 microcoulombs, right? 2 microcoulombs up here, minus 4 microcoulombs down here, 6 microcoulombs over here, all right? And what we're looking for, what is the magnitude of the force due to the electric field at QA, right? So magnitude of the force due to the electric field. Well, the force due to the electric field, if you remember, force due to the electric field, F equals, oh, just getting into math mode, F equals Q times the electric field, right? So in this instance, what we're looking for is F is going to be QA times whatever the electric field is due to the other pieces, right? And the electric field, all right, electric field in this case is going to be, we got QA, it's going to be E due to C, right, plus E due to B. All right, so we're going to have to add those two together. This is a vector problem. We're going to have to add those two vectors together to get the total force. And then once we have the total force, we're going to take the magnitude. All right, we're going to get the magnitude from the Pythagorean theorem. Right, calculate calculate the hypotenuse of this vector. All right, so the next question then is, okay, so this is what force is. The force is QE. We know that the E field is the sum of the electric field due to QC and QB. So now we have to start working on what are those electric fields, right? What are those electric fields? Okay, so let's take a look. What's the formula we start with? All right, E vec, the vector, the electric field vector is K onto Q over R squared. And that is in the R hat direction. What is the R hat direction? The R hat direction is a direction pointing directly away from the charge Q, right? So if we look at QC and we're talking about which way does the electric field point, or which way is R hat, right? R hat is in that direction. Now, because QC is negative, right, we're going to end up with, at the end of the day, our hat is that way, but the electric field, EC, right, is going to point back towards QC. So there are a couple ways to keep this straight in your head. One is to always remember R hat points away from the charge we're talking about, and then the sign of the charge takes care of it. The other is to always remember that the electric field points away from, right? If this is a positive charge, the electric field points away from it. But if it is a negative charge, the electric field points towards it. All right, that's the other way to remember this. So positive charge, electric field points away. Negative charge, the electric field points towards. Okay, so now here we are. We have EC is going to be pointing from QA back towards QC. All right, we can get the magnitude of EC from KQC over R squared, and that'll tell us how big this vector is, and the components, that angle out there is also 60 degrees, right? So there's going to be a piece that points straight back. There's going to be a piece that points straight down, all right? And then there's the magnitude of it. So let's go back over here and let's get the magnitude the magnitude of EC is K, and then magnitude of QC over R squared, right? K is 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. Let's see if I can get all of this in here. 8.99 times 10 to the ninth. Gonna have to make this larger by a bit, and I'm going to there we go. Okay, times 10 to the ninth. And then our units are newtons meter squared per Coulomb squared. All right. QC is minus 4. Is it 4? Yes, minus 4 times 10 to the minus 6 coulombs. And then R is 0.25 meters. 0.25 meters, and that has to be squared. Okay, let me move this around a bit, get to where you can see it well. All right, so this is EC, all right? 8.99 times 10 to the ninth newtons meter squared per Coulomb squared times the charge minus 4 times 10 to the minus 6 coulombs divided by the radius squared, right? Oh, and we're taking the absolute value or the magnitude of that charge, so because we're taking into account the direction on our own. All right, what does this equal? Well, let's pop open Excel. Okay, 8.99 to the ninth times 4 to the minus times 10 to the minus 6 divided by 0.25 squared. So we get an E field that is that's pretty large. 10 to the ninth, 10 to the minus 6. All right, that's 575 or 5.75 times 10 to the minus 10 to the fifth, right? 5.75 times 10 to the fifth newtons per coulomb. Okay. All right. So that gives us the magnitude of the electric field at A due to C. And we know, right, we know that it points this way. And we know that that angle is 60 degrees. All right? So that means what in terms of what are the components of this? Well, the x component is going to be negative minus this magnitude times the cosine of 60 degrees, because the x component points in the negative direction. The y component is going to be negative this magnitude times the sine of 60 degrees. All right? So that's going to break this vector into its two components. So we have E C X, right, is going to be minus 5.75 times 10 to the fifth newtons per coulomb times the cosine of 60 degrees. And Okay, now that my computer is ready to do things again. All right, let's get this. So I need that times the cosine of degree of radians. Excel uses radians, so I have to convert things to radians. So 2.88, right? 2.88 times 10 to the fifth newtons per coulomb, and that has a minus sign in it. Right? So that is the x component due to C. All right. If we want the y component, right? We've talked about that already. The y component. All right. Again, the y component, it was pointing down, right? The y component is minus 5.75 times 10 to the fifth newtons per coulomb times the sine of 60 degrees. Right? Okay. So let's go back over and let's calculate the sine. So we're talking about that times the sine of, and I have to use the radians again to convert 60 degrees to radians. Okay, so now we're looking at 4.98, right? 4.98 minus 4.98 times 10 to the fifth newtons per coulomb. Okay, so what have we done? Well, we started off by looking at the electric field. Let me just move this over here. There we go. All right, we start off looking at the electric field, and we knew we needed the electric field because we know the force is QE, and that the force is QA onto EC plus EB, where EC is electric field due to C, EB is electric field due to B, right? We looked at what the electric field equation is. It's KQ of R squared R hat, where R hat points away from the charge that's the source. Well, in this instance, we get the magnitude of that, and we work out because QC is negative, it actually points towards QC. And so we drew in, this is EC right there, right? And we got EC, and then we got the X component, and we got the Y component. So this is ECX, and this is ECY, all right? And that's what we have right here, ECX, ECY. And now we're ready to move on to the next piece, which is finding out what happens to the electric field due to B. All right, so I'm going to just copy this whole slide. And we're going to take a look at B. Because we're going to go through the same thing for B. All right, here we are. This was EC. Well, we're going to call that EB. We're going to stick in. We're going to stick in B everywhere, right? All right. Now, B, the charge B, is 6 microcoulombs, so that 4 becomes a 6. All right, let's go back over to Excel. Here's one of the reasons I like using Excel. I'm going to change the 4 to a 6 here, and 8.63 times 10 to the fifth. My apologies, my computer is slower than molasses. 8.63, right? Okay, so that's 8.63. Now, difference here, right? This is a positive charge, and the electric field points away from positive charges, right? Positive charge, electric field points away. Over here, this is a negative charge, right? Electric field points towards. So the electric field is pointing away from QB, right? That means it's pointing off this way, right? That means, and just like before, right? That angle is 60 degrees. Right? That angle is 60 degrees. So this is going to be EBY. This part here is going to be EB, right? X. So what does that change in what we did with C? Well, the X component is still pointing in the negative direction, right? So that minus sign is going to stay. But the Y component is now pointing in the positive direction. So that minus sign on the Y component is going to flip to a positive sign, right? So as we just convert from EC to EB, right? EB, all right. This is going to be, this stays negative, 8.63. All right. Fortunately, Excel has already calculated for us. So 4.32 is going to be the number here. 4.32. Oh, and it's still negative. I accidentally took out the negative sign. All right. Now, in Y, okay, the change in Y, not only did the 5.75 change to 8.63, but it's now positive. Positive 8.63. All right. Just going to make this positive out here. Okay. And the number, again, Excel is already 7.47. So this is now 7.47. All right. Okay. Now we have the electric field due to B and its two components at A, right? We've got the same distance, 0.25. The constant there is the same. The 4 microcoulombs changed to 6 microcoulombs, so we get our new result for the magnitude. Since this is a positive charge, we know the electric field points away from it, right? And then all we did in these next two steps was we got the direction, we got the components, the X component and the Y component of that vector. Now, moving down into the end, what do we need to do? We have to combine the two, right? We have to combine the two to get the total electric field. So again, I'm going to copy the slide. I'm going to go back up here to the B slide. I'm going to grab those components. Okay, come back down. We're going to take, I'm going to get rid of that for the moment. All right, and I'm going to just paste into here the components for B and C, right? So we have both EC and we have ECX, we have ECY, we have EBX, EBY. Why do we have to get all of this? Because these are vectors, right? These are vectors, and so we can't just add them without taking into account how the components add. You can see here ECX is negative, EBX is negative, so this is going to be minus 2.88 minus 4.32. So if we start looking at what is the total electric field in the X direction, right? So that's going to be minus 2.88 minus 4.32 all times 10 to the fifth newtons per coulomb. All right, so what's that going to be? Minus 288 minus 4.32 minus 2.88 minus 4.32 is minus 7.2. Minus 7.2 times 10 to the fifth newtons per coulomb. All right, that's EX. EY, we have to do the same thing. Now here's where, breaking up into components makes it even more obvious that we have to do that, because ECY pointed down, but EBY points up. All right, the X components pointed in the same direction, but the Y components point in opposite directions. So in the Y components, we have minus 4.98 plus 7.47, right, times 10 to the fifth newtons per coulomb equals, all right, so let's go over to Excel and get that. Minus 4.98 plus 7.47, I typed that wrong, 2.49 equals 2.49 times 10 to the fifth newtons per coulomb. All right, 7.47. Okay, so now we have the X component of the electric field, we have the Y component of the electric field, all right, and we need to get the total magnitude of the electric field. So the electric field total, all right, it's just going to be the square root of EX squared plus EY squared. All right, it's the hypotenuse, right? We have the X component, we have the Y components, we have two sides of the triangle. The length of the hypotenuse is A squared plus B squared square root, right? Okay, so let's get that. 7.2 equals that squared plus that squared. I need to go back and I need to take the square root of it all. The 10 to the fifth is common to everything. It factors out. 10 to the fifth squared, square root is 10 to the fifth. So that comes out easily. So 7.62. All right, what I get here is 7.62 times 10 to the fifth newtons per coulomb is the total electric field. All right, so that gets us the total electric field. Now we're asked for, where the question is, what's the magnitude of the force, right? And we know, right, we know that the force is just Q times the electric field, right? And since we're talking about magnitude, I've taken off the vectors. So QA, force on A, QA is 2 times 10 to the minus 6, 10 to the minus 6, all right, coulombs, times, here we have 7.62 times 10 to the minus fifth, no, not minus fifth, fifth newtons per coulomb, right? Okay, so 2 times 10 to the minus 6 times 7.62 times 10 to the 5th is 1.52. 1.52. At the end of the day, the units are newtons. Long problem. I know it's a difficult problem. That's why I wanted to go through this. And if you look at this in this page, where we calculated the x component, and here the x component, right? We're doing part of problem 8, and when we calculate the y components, we're doing problem 9, and problem 10, we're putting problem 8 and problem 9 together to go through the whole thing and get down to the end. All right, that's it for problem 10.